So in this video we're going to discuss Maclaurin polynomials. I've written out the key formula for a Maclaurin polynomial here. I'm going to be writing the polynomial as p sub n. Its highest order term is x to the power of n. And the coefficients are explicitly given here. Here is the coefficient of x, here is the coefficient of x squared, etc. And the notation which I'm using is that the function f with a superscript n in brackets and the function evaluated at x equals 0 corresponds to the nth derivative of the function as a function of x, and after you've calculated this derivative you then set x equals to 0 to evaluate these coefficients. So again, there is no x dependence because we have set x to 0 in the coefficients. The x's are here explicitly here, 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 etc. and here. And Maclaurin polynomials and their more general case of Taylor polynomials are of great importance in many fields, perhaps especially for numerical work. And in particular, the Maclaurin polynomial gives you an approximation to the function around the point 0 f of 0. So in other words, where x is 0, the function itself has the value f of 0, which occurs here. This is where our function has a good agreement. In particular, if we actually look at our equation here, and if we were to immediately just set x equals to 0 in here, then you would have f of 0 here, which is what we want, and all of these other terms would vanish. Now, what I want to do on the next slide is to show that not only is it sensible to choose these, but to explain why we have these other coefficients here. Having done that, I'm going to use two examples to show how we can calculate Maclaurin polynomials. So here I've summarized the basic idea. We want the function f of x and our Maclaurin polynomial p sub n of x to agree at x is 0 in the following way. We want them to have the same value, and we saw that what we wrote down a moment ago had that property. The function and the polynomial agree at x is 0. But we also want them to have the same first derivative. This is the first derivative of the Maclaurin polynomial evaluated at 0. This is the first derivative of the function evaluated at 0. Similarly, we want them to have the same second derivative at x is 0. We want the same third derivative at x is 0, etc., etc., up to we want them to have the same nth derivative at x equals 0. And it should be noted that there is an error in that for any finite polynomial it cannot agree with the n plus 1th order derivative, because p n plus 1, the n plus 1th derivative of an nth order polynomial, no matter where you evaluate it, is going to be 0. So for example, the third derivative of a quadratic is equal to 0. So just e.g., the third derivative of some quadratic term with some arbitrary coefficient, I don't know what it is, let me just call it cx squared, is equal to 0. So the polynomial, if its highest power is x to the n, its highest non-zero derivative is going to be the nth derivative, and beyond that the n plus 1th derivative, n plus 2th derivative, etc. of the polynomial all vanish, and that's an error. Now the error is very important and there is a great deal of mathematics known about it, but I'm not going to talk about that in this video. I'm going to talk about calculating the formula and how we can calculate the coefficients. So let's obtain the formula on the next slide. So the notation that we're using is that we're going to write the polynomial as a sub 0 is the constant term, a1 times x is the term that's linear in x, a2 times x squared, quadratic, etc., up to an times x to the n. And we want to require the following constraints on our function. So we're going to demand that the function and the polynomial agree at x equals 0. So we're going to demand that our polynomial, Pn, evaluated at x equals 0, and this is just going to be a0 because all the other terms are multiplied by x and will vanish. So this is a0. We're going to demand that this is our function evaluated at x equals 0. So this equation here tells us what the constant term is, and that was the result that we had when we wrote down the formula for the Maclaurin polynomial on the first slide. Our second requirement involves the first derivative, so let's now calculate the first derivative of our polynomial. So the first derivative of the polynomial, Pn of x, with 1 in brackets as a superscript. Well, the first term when we differentiate it is going to vanish. The second term, a1 times x, will just give us a1. So we have an a1. And then the next term, when we differentiate this, we're going to bring down a 2 in front of the a2 and change the power by 1 down to x. So we're going to get plus 2a2x. The next term we're going to bring down a 3, so we'll get 3a3, and then it's x squared, etc., down to n times a sub n x to the n minus 1. Now what we want to demand is that this evaluated at 0 is equal to the first derivative of the function evaluated at 0. And this evaluated at 0 is quite simple again, because in just the same way that all these terms vanished when we worked out the polynomial at 0, when we calculate the first derivative at 0, this vanishes, etc., etc., and we're left with a1. So what we have is that the first derivative evaluated at 0 is a1, and as we've said, we're going to demand that this is equal to the first derivative of the function evaluated at 0. So that is our second equation, that a1, the second coefficient here, is equal to the first derivative evaluated at 0. So our second requirement involves equating the second derivative, so let's calculate now the second derivative of the polynomial, and we do that by differentiating the first derivative. So we take this result and we differentiate it. So what we have is that the second derivative of the polynomial as a function of x is given by, well, the derivative of a1 is 0 because that's a constant. The derivative of 2a2 times x just gives us 2a2. And then the next term, when we differentiate this, we bring down a 2, and we have plus 3 times 2 times a3 times x, plus other terms times n minus 1 times an x to the n minus 2. And now we want to evaluate this at 0, and again this is very simple because all of these terms will vanish because they're all multiplied by x or higher powers of x. So therefore we have that Pn2 evaluated at 0, so our polynomial, the second derivative of it evaluated at 0, is 2a2, and all the other terms vanish. And this we want to equate to the second derivative of our function evaluated at 0, so that means that a2 is equal to 1 over 2, and then it's the second derivative evaluated at 0. And I'm going to write here 1 over 2 factorial, because that is going to be helpful for the pattern we have later on. Of course, 2 is equal to 2 factorial. So at this stage we've calculated the first three coefficients. We've shown that a0 is equal to our function evaluated at 0. We've shown that a1 is the first derivative of the function evaluated at 0. And we've now shown that a2 is 1 over 2 factorial times the second derivative of the function evaluated at 0. And just to show that it really is factorials that occur, I'd now like to calculate A3, and to do that we're going to need some more room. So for our next requirement, let's calculate the third derivative, Pn3 of x. And the first term here is a constant, so it vanishes when you differentiate it. This term is proportional to x, so when we differentiate it, we'll just be left with the coefficient 3 times 2 times a3. 3 times 2 is 3 factorial, so I will write that as 3 factorial times a3. Now, when I initially wrote the polynomial out, I didn't write an x to the fourth term. If I had done that, I would get the term that I'm going to write down next, and I think that's a nice exercise to write it down here, a4 times x to the fourth, and just trace it through this differentiation, and just to verify that what you would then get is 4 times 3 times 2 times a4 times x. And then there would be other terms, and the final term is given by the derivative of the last term here, and that involves bringing down a factor of n minus 2 and reducing this to n minus 3. So what we get is n times n minus 1 times n minus 2 an times x to the n minus 3. And now what we have to do is to set the x to 0 in here, so that we can calculate our derivative at x equals 0. So the third derivative of our polynomial at x equals 0 is 3 factorial times a3. All the other terms written here vanish, and that is going to be equal to, by our requirement, the third derivative of the function at x equals 0. So this tells us that a3 is 1 over 3 factorial times the third derivative of the function evaluated at x equals 0. And replacing in this equation 3 by n is the completely general result for the equation of the coefficients. So we have the coefficients are given by this form, just replacing 3 by n. And as I said, it's a nice exercise, perhaps again, to verify this for n equals 4. So at that stage, we can substitute these coefficients here, 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 and here into our equation, and we have derived the result for the Maclaurin polynomial. And on the next slide, I'm going to write out the result and use it to calculate an example. So here I've written out the formula for the Maclaurin polynomial. You take the function evaluated at 0. You add the first derivative evaluated at 0 multiplied by x. You add the second derivative evaluated at 0, divide it by 2 factorial, multiply it by x squared. Repeat with the 3, x cubed, up to n, where n is as far as you go. And I now want to give 2 examples, and on this slide we're going to look at the example where we want to approximate the cosine function by a polynomial in the vicinity of x equals 0. So we need to work out what the function is at 0. That's the first term in our Maclaurin polynomial. And the function, the cosine function evaluated at 0, is of course 1. We then need to calculate the derivative of the function, and the derivative of the function, the derivative of the cosine, is minus sine of x. And we're going to need to evaluate this at x equals 0. So we're going to need, in other words, to have minus the sine of 0. But the sine of 0 vanishes, so this also gives us 0. We're now going to need the second derivative, and the second derivative is the derivative of the first derivative, so it's the derivative of minus the sine of x, and this is minus the cosine of x. And this evaluated at 0 is minus 1, because the cosine of 0 is 1. We can carry on and calculate the third derivative. The third derivative is the derivative of the second derivative. So there's a minus sign here. The derivative of the cosine is minus sign, but multiplied by minus sign, it's going to give us plus. So we have plus the sine of x, and this evaluated at 0 vanishes, because the sine of naught is naught. We then calculate the fourth derivative, and the fourth derivative is the derivative of the third derivative. It's the derivative of the sine of x, and the derivative of the sine of x is the cosine of x. And evaluating this at 0 tells us that the fourth derivative at 0 is plus 1. So now we've calculated some coefficients. I'm going to stop here. One could, in principle, carry on to higher terms, but we have enough for a moment, so we can now insert these into this. So what we see is that the first term is going to be 1, so p, and I've gone up to 4 of x for the coefficients of the cosine function. It's 1. The next term here vanishes because f1 of naught is 0. The next term, f2 of naught, we've seen is minus 1. So we have minus 1 over 2 factorial times x squared. The x cubed term also vanishes because f3 of naught is 0, so this term vanishes. The next term is going to come from the f sub 4 of naught term, and that is 1. So what we're going to have is plus 1 over 4 factorial times x to the 4th. And I'll write down the next term and leave it for you to calculate and to verify it as an exercise, that you would get minus 1 over 6 factorial times x to the 6th, up to whichever order you're going on. So that's how to calculate this example, and I will make a comment on this example, which is that you notice that here we only have even powers of x, and this is because the cosine function which we are studying is itself an even function, and therefore we would only expect to have even powers of x. So at that stage I'll stop this example and move on to another one on the next slide. So I've written out here again our Maclaurin formula, and we want now to use it to calculate the Maclaurin polynomial for the function 1 over 1 minus x. So our function f of x is 1 over 1 minus x, and that means our function evaluated at 0 is 1 divided by 1, which is of course just 1. We now want to calculate the derivative of this, so f1 of x, and this means the derivative of 1 minus x all to the power of minus 1. So I bring down, using the chain rule for powers, a minus sign. I then have 1 minus x to the minus 2, and from the chain rule I need to multiply this by the derivative of 1 minus x. And the derivative of 1 minus x is a minus sign, and a minus times a minus gives us a plus sign here. So you may want to verify this step carefully with pencil and paper if you need to. And this evaluated at 0 tells us that the first derivative at naught is plus 1, because here we have 1 minus naught, which is just 1, 1 to the minus 2, it means we're dividing 1 by 1 squared, and that's just 1. We now repeat this, and the second derivative is a function of x. Well, again, from the chain rule for powers, we bring down a minus 2. So we have minus 2 times 1 minus x to the minus 3. And now we have to multiply this by the derivative of 1 minus x. That's what the chain rule tells us to do. And the derivative of 1 minus x is a minus sign. So this makes this overall sign plus. So therefore, the second derivative evaluated at 0 is 2. In the same way, the third derivative as a function of x is going to be, well, we already have a 2 here. We'll bring down a minus 3, so we're going to get minus 3 times 2 times 1 minus x to the minus 4. And then we multiply this by the derivative of the brackets, gives us a minus 1. So yet again, as you're probably expecting, we have a plus sign. So therefore, f3 of 0 is equal to 3 times 2, and 3 times 2 is 3 factorial. And we can see that there's a definite pattern emerging here, and in general, we have that the nth derivative of this particular function evaluated at 0 is n factorial. So therefore, the Maclaurin polynomial for our function 1 over 1 minus x is, well, f0 is 1. The first derivative gave us the first coefficient, and that's right down here, and that's also 1 times x, so it's plus x. The next term gives us the second coefficient. There's a 2 here, but it's 2 divided by 2 factorial, so they will cancel and leave us with 1, so it's plus x squared. The third term, there are 3 factorials which cancel, giving us an x cubed, etc., up to x to the n. So this function here, 1 over 1 minus x, can be approximated by this polynomial here, this Maclaurin polynomial, and if you take large enough n, you will get a good approximation in the region around x equals 0. And at this stage, I'm going to stop the video.